Hello, we're back again and we are continuing in part 4C. Let's see if we can get our file. I'm going to program again. Think what's going on. Let's see if there's anything shaken, misconnected. No, that's not the case. That's not the case. Okay, it doesn't sound right. I'm going to slow this down. Let's see what is not matching in this code here. We take our clock, bring it down to some 62 Hertz, and we say pulse count, and we zero out when it's equal, we increment when it's not, and let's see. So this part is working fine. Our counter is recognizing exactly how much to count. The LED pulse is getting to the right. Let me see if we can change this frequency. Maybe the frequency is a bit too high. Maybe let's bring it down to 95 Hertz. And let's compile. And I'll come back again. Folks, this is complete. However, I have found a small mistake in my code, and that is basically where the counter is counting up. I should have a second condition to confirm that it is not overflowing. So what I mean by that is that at this stage here, where the counter is matched and we are pulsing, I have in my previous codes that I was testing and I was executing well, and in my previous code that I tested and it worked flawlessly, it actually had a condition, and that condition was basically to prevent the counter from overcounting. Not sure why that's the case here. It should just go into a simple counter mode when it's not equal to the switch, and yeah, so that's basically what is happening. Probably that's what's happening. So what I'm going to do is make it exactly as my test code, and what we will do is we will test this. Let's see. Let me focus here. So now this should only count up when it's either higher or it's at 0 position. So when the first condition is true and makes it 0, it will come down and start counting. And yeah, that should be the case now. Let me make sure is there another reset. Am I doing another reset of our clock? No, I'm not doing any other resets. So I did, however, save one pulse output in my previous program. So instead of housing a separate process just to pulse out, I'm also doing the same process. This process right here, I'm just executing it here. Nothing drastically or wildly different from my current code. This way. It's much more cleaner and much nicer. You can clearly see exactly what's going on in the code. Exactly where we are dividing the clock. We are then dividing it further by comparing it with the switch, and then we are coming down to the next process where we are flipping our LED and motor pins. So yeah, that basically should be it, unless I have a wiring problem in my code. I'm not sure. Maybe that's the case, but let's see. What I'm going to do is execute this one more time. Let's save this. And if this is not the case, then definitely my wiring has some kind of a issue, and I have to troubleshoot that. And yeah, we'll come to that when this compiles and we download. Then we will see exactly what is happening. Okay, let's pause this video here and come back to it when the compilation is complete. Okay folks, so it is complete and we are going to upload this code. Let's see what is new. Okay, something is different right now. Let me see, this frequency is a bit different. So I spot another mistake. So folks, I have another correction to make here. I see as, let me close this first. Okay, so let's move this here. There we go. Okay, so essentially we built the code, we built the logic. What is happening is that process is using 762 hertz as a trigger. Remember, the pulse is going up and down, basically like this. So the process is reading at every point. It's triggered here, then it's triggered here, then it's triggered here, then it's triggered here, then it's triggered another, and so on. So what's going on in this process is that every time the pulse comes in, high or low, this is triggered. The count goes up, and we get a sequence output, similar sequence output here. So if you could imagine twice this process changes the count, compares, and pulse out. And this process right here is looking for rise up only, only at the high end of the pulse, basically at this side of the pulse. It doesn't care about this side of the pulse. So this is sequencing on high and low, and this is sequencing at high only. So the offset between the two is created by this low side. This is counting faster, it's going quicker, and this is trying to go at the pace and only going to look at the higher edge, or the bit high or bit 1. So what's this outsync is causing our output to try to go faster. So this outsync, so this out of sequence is mismatching the two processes, and our output is more unrhythmic, I must say. But yeah, I believe you get the point that our pulse output process is sending more pulses out, and it's comparing at a faster rate, and it's changing. Because of that, it's changing at a much different frequency that we intend to change. So it's not changing at a lower frequency, it's trying to go higher and lower, higher and lower, higher and lower every time. Yeah, I have to put together a good note. If you want further explanation, you can put down in the description, and put down some comments in the description, and I can figure out how to explain this. So okay, let's bring this into the rhythm and just look at the higher pulse, or higher input of the pulse. So, and avoid any lower end of the pulse. All right, let's do it this way. So let's do that. So this way, now our logic will only execute at higher pulse one time only, not twice, and this will be in sequence with the output as well. Okay, and I believe this is, oh, I need to comment this so we can, this is commenting out. I wonder if I can use a different key, but that will be, no, let's not play with this. Let's continue. I am just not trying to focus. Okay, let's focus on our objective. And again, we'll come back to this when this compiles. So folks, the compilation is complete. I believe it is, yeah, this is complete. I'm going to download it one more time. Not this. Okay, let's program it again. Okay, that's flashing. Yes, this is the right rate. Okay, there we go. Going to close this. Let's go back to the program. So the code basically, as I mentioned earlier, that this the process that we're generating, the process where we are generating this pulse was firing at two different times, one at high and one at low, and both times it's counting up and comparing as well, counting up and coming back. I believe not just as not only that it was out of sync with this process, but also I'm very sure now I don't have a I don't have let me see if there's the right word for it. I cannot graph this into a digital format and exactly see what my pulses look like. But all I can do at this time is predict exactly what the pulses might have looked like. That not only that it was going high and low, but because of this sequence here, where it is comparing against the switch, the zeroing out was also throwing this out of sequence where the frequency was the output frequency was random. Basically, the output frequency of this SW pulse out was more random than uniform as we want it to be. So I think that's what was going on. But if I had a let me look up the device name and come back again. So if I have the oscilloscope, I would have understood exactly what frequency or what ranges of frequency, which ranges of frequency was this process was generating. So essentially now it's putting out more uniform output. It's not random, and as you can see, we can control the output by selecting different modes of this current driver. Okay, so let's test our switches. So if I go to highest, it goes really slow. So essentially this was at 762 Hertz. I can slow it down to 1. This is 3, and this would be 4. And all 15 is, this is the speed. So basically, yeah, we can now change or control our frequency and the motor output using a simple switch. Okay, so this was the next objective. So this was the objective. We have achieved that. We have control over the motor, and now what we want to do is go into our next. And now what we want to do is go to our next objective, which is basically to control the speed from the HPS side and write out to the memory and read from the memory in this FPGA, and then apply that speed to, or apply that frequency to our motor. So okay, so let's prepare for this for the next objective. I'm not sure I recorded this video, so I want to put this up on view after the download. We can control the output by the switches. slowest would be 15. All 0. This is the 762 hertz. So 1, 2, 3, and 4, 5, 6, 7, 8, 9, 10, 11, I believe this is going to be 12, 12, 13, 14? Oh, we did from 0. Okay, so this is 15 basically. 15 states. Essentially, that's basically the control we can have from 0 to 15. Okay folks, so now I have a baseline program ready, and the program is doing its job. As you can see, I have a good working program controlled by the switch. Well, at this time I've loaded a different program, but in any case, the overall code that this file has generated, I can reload it. Let's reload. Maybe that's a problem. Let's see if we can reload our code overall. And yeah, there it is. Okay, so yeah, it was running a default program. I apologize for that. But what I want to say is that this is our baseline program, a VHDL program that we have created so far, using the 50 megahertz clock. We're bringing it down to 762 hertz, and then we are further controlling that to contain that. Oh, hold on. My pulse counter, I think something has happened here. Let me reopen this. I'll reopen this. Hold on. Okay, yeah, there you go. I think I did a control, maybe undo a command somewhere. But anyways, so as you can see, clock divider, then we bring it down to 762 hertz. And as we are doing that, we are also looking at our switches and watching for the 0 to 15 count from our switch end, and then comparing that switch configuration to our internal VHDL counter. Where it matches, we then put out a pulse at that instance, and using that pulse we then pulse the light and also the motor pin. So this is our baseline program. Now what I want to do is take this program and modify it to work with the HPS. Okay, now the first step what we want to do is basically understand some basics of the HPS. Let's see, I'll try to explain as much as my understanding allows me, and if there's any question, or if during the video I'm unable to explain, what I'll do is I'll put that further explanation in the video in a text format. Okay, let's see, let me find a good slide for us. This is from the Terrasic documentation manual, and I am looking for my HPS and FPGA explanation. This is for the HDMI, and there is one slide I remember that we had. I know I've seen it. Okay, there it is. Yeah. Alright, so essentially, let me turn off the video. apologize. I keep forgetting about this video. Sometimes it just freezes up, sometimes it runs and overlaps the content that I want to share. Anyway, so in the manual you'll see that in a single Cyclone 5 chip you have two different environments. You have a FPGA and HPS. HPS is running the Linux environment, and FPGA is FPGA, basically gate logics, uh, uh, basically gate controllers, and that you can program. Now think about this, that what we want to do overall in this project what I want to do is basically send the message to this my drive. Let me bring this back in the view so you can understand. What I want to do is basically turn this into my motor driver, and it's going to control three different motors: right ascension, declination, and the focus. And each one, what I want to do is I want to name, by name I want to control its speed, its position, its direction, etc. So with those in mind, with those objectives in mind, what I want to do is I want to have a good handle from the HPS to receive commands and process those commands, and then at the end put out instructions for my FPGA, which then FPGA can take and execute. That's basically the whole plan. So if you look at this architecture, HPS side has the UART access, so it can directly listen from the UART connection, and there is only one UART. Yes, yeah, there's only one UART, the one that we use for the console. So eventually we have to turn off the console to listen in, which we did in the first or second part of this whole series. So HPS is going to receive the instruction, it's going to process, and it's going to figure out how many steps, how many what speed, what direction, and write that down to the memory. And I'm looking for that memory here. It's not shown in this view, but just assume right now that there's a memory that is shared between the two, which is read through a Avalon driver. If I come across that picture, let me see if I can find that Avalon driver here. Oh, not Avalon. I apologize. This is a it's all written representation. Well, DDR3. Here's the Avalon map. Okay, so here you go. So what I'm going to do is program a C++ program in the HPS. It's going to receive instructions, and it will then write out to the Avalon memory map location. FPGA will read it and then execute the instruction, basically controlling the motors, which is in our case, in this case, will be GPIO, and it's not shown here. Of course, there's always some piece that's missing. Let's see if there's a better representation. No, there isn't. No, there isn't. Okay, let's stick to this representation. So FPGA has access to the GPIO. It's going to control the motors. HPS is going to pass on the position, speed, and direction to the FPGA. So essentially right now what we want to do is we want to control the speed of the motor. That's what we're doing in our baseline program. So what we will do is, from the C++ code in the HPS, we will just write out the 4-bit output to the FPGA. Now with that 4-bit output, we will take that in FPGA and basically join that 4-bit output to this process right here, where what I'll do is basically I'll create another process, and I'll keep this switch control in there. So in case if we run into an issue, we can test our switch output frequency, and if that's working, then obviously we know that the HPS side isn't working. So that way we can debug in a sense. Okay, so that's basically what the plan is for this part. Okay, so let's begin this step. All right, in this step, what we want to do is program our HPS, or get our, sorry, what we want to do is prepare our FPGA side to read from the HPS. Let's do that first. Okay, in order to do that, the component we need is it's called QSys. It's basically a designer platform. The portion of the name is on the window. Basically, the other side says platform designer. So this is basically a platform designer. What this allows us to do is make connections to the Avalon memory, and using those connections, just read the memory at will, or at convenient intervals. So there's no special programming needed to figure out when to read. The Avalon memory map will figure out when to do that. All we do is we just read the output from the Avalon. Yeah, so it's called Platform Designer. Okay, and remember, this is the button for it. You'll see a tooltip showing up, which is not, okay, never mind. But it's Platform Designer. Okay, so in my case, what I've done in order to fast track this whole project, I did try to discover various different paths in order to create a robust project and a good understanding of the whole environment. And I did look into creating starting from a blank platform designer and working backwards, and try to release that to the board. But I ran into multiple issues doing that. First one, the top one, was the SD card itself. The image, the 3 different images provided from the Terrasic website, and the 2 other images I acquired from the Zhangman website that I shared earlier, they all had issue one or the other way. Even the one that we're using right now, I doubt that all the features actually going to work in this SD image. So for now, lightweight works, and I'm just going with it at the moment. So that was one problem, SD card. Another problem, a second problem that I faced, was the different variables, multiple different variables that I had to configure. For example, let me show you what I mean. This is the component we have to use. It's called Cyclone 5 Hard Processor System. Through this component, we can read the Avalon memory output, the lightweight memory output, and then we can pass it on to our FPGA. The problem was that it has so many different connection points and clock configurations, peripheral configurations, that I ended up making mistake one way or the other. Let's put it this way. Like, for example, it's just like if you have a system of 12 different systems basically, and if just one system has a problem and they're all lined up in a series, you will end up have a problem in the combined system. And that's what I kept running into. Apart from just this one tab, as you see, this has opened. So when you double click on this component, you will get the option to configure its interfaces, peripheral pins, then clocks inside the SDRAM, timings, etc. Let me just give you a little bit of a brief overview. That these are all the peripherals available to the FPGA. And these are the clock configurations for input and output, and SDRAM side, and even the SDRAM has, you can see, multiple other tabs that I have to configure. So in order to avoid further setbacks or more setbacks, what I did is basically follow the GHRD, which is basically, I followed other videos online, and other users, D10 users, have also done similar, have taken similar paths. So I stick to that particular habit or process, and basically to streamline this development, the project of this, basically streamline this project overall. So okay, I'm going to close this, and what I want to do, instead of starting a blank one like this, what I will do is I will copy the GHRD. GHRD is the golden, I believe that's what it stands for. It's the golden example that you will use, or you will get from your CD, from your D10-nano CD, or the resource, available resource from the Terrasic website, and it will give you a bunch of programs. I'm going the wrong way here. It's in Altera. I saved it in a different location. So it will give you an ISO of the CD, which I have extracted all here, and in there you'll see these example projects. Oh, not the example projects, demonstrations. Apologize there. Demonstrations. So inside the demonstrations, our focus is SoC, FPGA, and in the SoC FPGA we have this GHRD, which has most of the options enabled in its QSys program. Okay, what we will do, we will take the QSys file, which is this file, SoC system QSys file, and we will copy it to our project. I don't know, did I copy it before, but for the sake of demonstration I will do it again. D10-nano, this is our project location, our second attempt of this video. Yeah, okay, it's copied now, and this is the only file in this project folder. Now what I will do is get to our, I don't want to reopen another QSys window. It can open multiple windows if you want to know, and if you want to just copy one from the other, you can just take the whole file and then modify your file and make sure that it's saved to a different environment, or the path, the project path changes for that file. But eventually, when you do save this, it will change the file paths. So for our case, this is our project file for the QSys environment, and what now we will do is we will open, do not save the current one, open the one we copied over. There will be some let's say prior version or older version configuration in there that it will say will be upgraded. So let's see if it, in our case it does, and yes, there you go. So it basically just telling us that I upgraded all these different components. They were programmed in a older version of QSys. Okay, so this is the GHRD configuration. Right now, this is not associated to our project yet. All we are doing at this point, it's looking at it, and we are going to start trimming it down for our use. Right off the bat, what I want to do, I did give you a little bit of peek into the properties of the HPS. You can try the same for all the other components, but I want to refrain from doing that because it's just going to prolong the length of this video. So what I want to do is focus on the main objective of this video and start trimming down this. So basically what we want is two components in our file, this HPS component and the clock component, which is down here. Let's see, let's start removing. All you do is basically click the upper level of that component or the top level of that component and hit delete, and that will delete that component from your QSys project. So in what I essentially wanted to say was, this is a separate project file at this time. It will become part of our project, our VHDL project, but right now it's a separate project in itself. So we will configure it for our need, and then when it's ready, we're going to include it into our main program. So JTAG UART, we don't need that, we don't need that, we don't need that, we don't need that, we don't need that. And this has to be up here. Sys ID QSys, don't need that either. All I need is the clock source, and for the sake of sequencing, it should be at the top. This will be our 50 megahertz clock 50. And let's see what we can do here. Okay, another thing what we want to do, remove my video for now. Another thing I want to do is remove all the other items from here, like interrupt requests. There's no need for that. AXI clock, I don't think I need that. I have to configure. I may have to check my test configuration. For now, what I will do is keep these. Yeah, hardware events. I don't need hardware events. I don't think I use these at all. I know for sure. Anyways, I know for sure that I will use only the lightweight. So I'm going to disable the other two interfaces. Basically, these are the bridges. As you can see, the lightweight is, oh, it's a bit slower. Sorry. Hold on. Yeah. Okay. So these first options are basically fast memory access, and you can assign up to 128 bit in one chunk. You can use that chunk whichever way you like, but the whole chunk of 128 bits or 64 bits or 32 bits is going to be available to you in that one connection. So further down, I'm using the lightweight, which is only 32-bit. They say it's a bit slower, but for my program, I don't think it's a concern. I've already tested my code, and it does what it does, and I don't see a issue with that. Another thing I want to do is I don't want to have any of these debug and cold reset requests. I'm not using any of these. There you go. Sometimes it's a little bit slower. Interrupts, I want to disable those as well. No interrupts needed. Okay, what else we want to do here? peripherals. I can keep all the peripherals, although I'm not using any of these. Let me see. I2C not using. UART I'm not using. SPI, SD, MMC controller. There is a need to keep SDRAM, as I understand that SDRAM controller is going to allow us to make that Avalon memory connection. Not entirely sure about that at this time. I have to do some other tests to confirm that. For now, I'm moving on with this project, and I'll scale it. And during the scaling, if I run into an issue, then I will look into it. But for now, my focus is to complete this project as quickly as possible. So, okay, SDRAM, zero clock data. Don't need any of these, but we do have to keep them in there in order to allow the lightweight to send our data. Okay, next thing is we have our Cyclone 5 connection, we have the clock. We want a output from this HPS component, which is LP PLL. I believe it was something related to the PLL clock. PIO, yeah, not PLL. So peripheral input output, that's what we need. Okay, here. Now one thing you want to understand, this input and output. What is input to the HPS? What is output from the HPS? So this is the output. Remember, we're designing the FPGA site. So for the FPGA to receive data, we want that data to be an output, because it's receiving, it's taking the data from this connection. So it will be an output. For our case, it's going to be just 4 bits, and we could go up to 32, but we don't need to, and we can do a finish here. Alright, and we want a clock connection, reset connection, S1 connection. Those 3 connections we need. Clock and reset, I don't think we need that here. Oh, this is a reverse reset, don't need that. And external, okay, so now we have the points. What we want is the connection point we read from, and essentially this is our connection point. It does not connect to anything. Do not connect to anything. It remains floating just like this. The QSys figures out the different pieces in here. So AXI clock, there are clocks that are still dangling in connection. I may have to bring that in and then remove it another way with another method. Let's see if I can. How can I remove it without? It does this, so let me bring it again. Oh, leave it in there. This one went away. I'll do the same for this guy. And then before I remove this, I will disconnect this clock. What I did, I just click this, and you can see that this has turned gray. Now this has turned gray. must be connected. Yes, it must be, but I don't want to. I want to remove this component entirely, and unused, set this to unused, and now it should disappear. Okay, yeah. So we are in business now. 50 megahertz input is going to be used by HPS, and that's going to drive the whole series of events here. Alright, so this is complete. Let's do a save as, and I'm going to save it as in the same location on the same file. Hit save as, overwrite, yes please. Now this file knows that it resides in this folder. Okay, so that's one piece. So that's it. That's basically it. Before I close, yeah. Oh yes, one more thing. I am getting ahead of myself here. So the external connection, we want to bring this to our code and read it basically. So in order to do that, we want to export that component. We have to double click, and here you can see that PIO external connection, blah blah blah. What I want to do, actually rename this. Let's do a rename. This is gonna be our HPS to FPGA lightweight. Okay, lightweight. And now when I do double click, external connection ext and ext out. I'll just do out. Okay, so F, no, doesn't like caps. Okay, fine. This is a lightweight. Lightweight out. Alright, so I'll do a save as again. Save as please. Yes, please rewrite it. External connection, good. Now, before I proceed, there's one other thing I want to point out. The base address and the end address. As you can see that we're using only the first 4 bits of that address, which is F, 0 to F, and it's only one connection point. You can have multiple outputs. Basically what you can do is you can for every single one you can say I want additional 8 bits or maybe even a full 32-bit output. And if you have multiple of these, you will have to assign a base address, and that base address becomes your contact point in your C++ code, which I will talk about when we get there. But essentially the base address, the starting base address, becomes the key point to making a write connection from the C++. Reading is going to be easy because this is our reference point in FPGA. All we do is just read it from this export point. Okay, so now this is saved. Now you click on the generate HDL, and I don't want Verilog. I don't want Verilog. Please don't. I want VHDL. Make sure that your path is correct. SOC system is our QSys output file name, and this will generate. Make sure that there are no errors before you do that, because it's not going to let you generate this HDL file. Then this is the key point of this project component, that you generate the HDL, and this compiles a series of other files which will we will then include in our, not all the files, will just include one file, but that one file will allow all the other components of this project to be included in our main project, our VHDL project. Okay, continue. It's taking a little bit of more time. I may have to stop the video. I don't want to record lengthy videos. They're difficult to edit. Very difficult to edit. I'm going to stop here and continue as this completes. Okay folks, this finally completed. No issues, some warnings, but nothing red. It's all just yield. Okay, so we will close this, and before we finish, we want to get a instantiation template. This is essentially your include file. First, you're going to include the QSys project, but then in order to make connection to your connection points in the VHDL, you must include these components and then make connection. So basically, this is the component, the SOC system file that we generated. This is the component for that file. All the declarations, the bit lengths, and then the port maps for each bit where it's going to map. Don't worry, this is something, it looks very difficult, but maybe intimidating, but it is not. But trust me, this is very straightforward. Just have to keep calm and take steps one at a time, and you will get it done. So what we will do is we will copy this whole window, the component part and the port part. Close, finish, and when it's finished, it gives you a little instructions that hey, you can include the QIP or SIP into your project. You can also, FYI, other than this, I've actually used the QIP include. You can also include the QSys project, the one that we actually generated and did will trim out and modify. You can take that file and include it into your project, and that will also include the complete platform designer project into your FPGA project. So this is a good hint. So you can, in whichever direction you want to go, it's up to you. I use QSys, so I'm going to do that. Okay, so that file is generated. Before I get to anything else, so I'm going to copy paste the component and the port maps into our project. The component portion goes into the begin section in this architecture. So, before the begin section, yeah. So right where you declare your signals, your other components, goes right here, and this portion goes into your main code underneath begin. Okay, we're not done yet. This is just one step towards configuring our project to read from this one little point right here. HPS to FPGA LW out export. I noticed that no matter what I... Alright folks, I have to cut the video here again. So I will stop the video, and it's just too much to edit, and I cannot go through each and every piece and edit the blanks out, try to squeeze the video. I've just basically given up on editing. So I'm going to stop the video here. We'll continue in the next one. So see you in the next part. Stay curious.